Prajwal and other people? Yes, somebody asked to solve that 2 into sink of 2t, finding a Hilbert transform. So you want me to do that, or shall I go ahead with this complex envelope? Yes, Prajwal.
Sir, we can solve it at the end of the class, sir.
Okay, okay, fine. Yeah, that will give you the continuity with the existing one. Fine. Thank you. So, okay, just we'll have just a recap of what we have discussed yesterday about the complex envelope of the bandpass signal. So, what I did is first I took the bandpass signal spectrum, right? I said what is bandpass signal. Then I wrote the spectrum of the bandpass signal, right? Then I found what is the pre-envelope of this bandpass signal, right? So that is done by with the time domain expression and as well as with frequency domain expression. Then since already I know what is S cap of F, I found the magnitude spectrum of S cap of F. Then I multiplied with J just to find J into S cap of F. Then I have added S of F and J into S cap of F to get the pre-envelope of the bandpass signal. So after getting that, what I did, I just shifted the pre-envelope of the bandpass signal by minus FC, okay, by using frequency shift property. So I could get the complex envelope of the bandpass signal, right? Hope this is fine. So this is what the pre-envelope of the bandpass signal. By shifting this by FC, right, that is by minus FC, I call that as a complex baseband signal. So mathematically, I express this complex baseband signal, complex envelope of the uh, baseband signal as what? S plus of t into e power minus j2 pi fct also I can write, or where s plus of t is this, right? S of t plus j into s cap of t into e power minus j2 pi fct. And in terms of just pre-envelope, I can express s plus of t is equal to s tide of t into e power j 2 pi fct. I said this s tide of t is known as the complex envelope of the bandpass signal s of t. Okay, so till this we were there. Okay. Yeah. Yeah, just I can draw the final diagram for this complex envelope of the bandpass signal as what? So this is the F, and let me this is my y-axis, right? So change the color. I said this is with W and this is with minus W. I can okay, so yeah, so this is my S tide of T, S tide of f, it is in, since it is in frequency domain, I can write this as what? Complex envelope of the band pass signal. Okay, so what will be its magnitude? It will be of 2. 2 into S of Fc I can write. 2 into S of Fc. Okay, fine. Uh, so I said S tide of T, right? S tide of T is what? Is the S tide of T is complex baseband. I said baseband signal is also known as low pass. We can write bracket as low pass equivalent of what? Equivalent of the band pass signal S of T. I just say BP signal, okay? BP signal means band pass signal S of T. Okay. Hope noted, na? If I scroll up, is it fine? Yes, if I scroll it up, is it fine?
Yes, sir.
Yes, sir.
Yeah. Okay. Yes, so what we have observed from this is that is what I wrote S plus of t is equal to S tide of t into e power j 2 pi fct, right? So just I will say the real part what we observed is the real part of so S tide of t into e power j 2 pi fct is equal to what? Just I'm substituting the value of S tide of t I'm writing here. So real part of S tide of t is what? Anyone of you can say what is S tide of t? What I can write for S tide of t?
S of t plus j
S
into
S of T.
Yeah, S of t. Yeah, continue now. Plus j into S at of t, right? This is entire thing is multiplied by e power minus j 2 pi fct, right? Then the next term it is e power j 2 pi fct is there. Just I substituted the value of what? S tide of t here. Hope you understand what I am doing. Just I substituted the value of S tide of t as what? S of t this much. S of t plus j into S hat of t into e power minus j 2 pi fct is the value of S tide of t. Okay. So in this, what is the real part of this? Yes, what is the real part? Shall I write? See, e power j minus 2 pi fct and e power j 2 pi fct will get cancelled, na? So can I write the remaining term, that is real part of S of t plus j into S cap of t? Is this fine? Right? So which is equal to what I can say? Real part of this. What is the real part in this?
S of t.
S of t. Okay. So S of t is equal to what I can say, real part of S side of t into e power j 2 pi fct. So this is my original band pass signal, what I can say, right? Yes or no? This is my original band pass signal. Okay. Okay. So with that, what I can write is, therefore, I can write S of t will be equal to the real part of S tide of t into e power j2 pi fct. Okay. So I said this is my what? Band pass signal, right?
Sir, can
This
you
is my band pass signal. Yeah. Yes, ma.
sir, can you scroll up, sir, little?
And this is, yeah, I will scroll up. So just I will complete this. So I said this is my what? Uh, yeah, this is my complex envelope of the band pass signal. This is my complex envelope of the band pass signal. Yeah, you want me to scroll up? Yes. Yeah, what I said is, I said S tide of t is the complex baseband equivalent of the band pass signal. Then what we observe is the real part of S tide of t into e power j2 pi fct. Okay. What I can write here is, yeah, let me write here and observe that. Observe that. See the real part of S tide of t into e power j2 pi fct. I'm just writing this and I'm substituting the value of what is S tide of t. So that is S of t plus j S hat of t into e power minus j2 pi fct is the value of S tide of t, and then e power j2 pi fct I'm writing as it is. So e power minus j2 pi fct, then e power j2 pi fct will get cancelled. So I'm writing the rest of the part. In that real part of this one is what? S of t. So that is my original band pass signal I said. So I am rewriting that one only. So S of t is equal to this real part of S tide of t into e power j2 pi fct. Yes, is this fine?
Yes, sir.
Yeah. Yeah, somebody is asking something? No. Yeah. Shall I scroll down?
Yes.
Yes.
So I said S of t is our band pass signal, which is equal to this seconds. So S delta of t is the complex envelope of the band pass signal. So therefore, what I can say is the complex envelope, right? The complex envelope S tied of t of the band pass signal, S of t is the what? Complex low pass signal. What I wanted to write is therefore the complex envelope therefore the complex envelope, what is the complex envelope? S tied of t, okay, complex envelope of the band pass signal, complex envelope of the band pass signal. What is that band pass signal is? Band pass signal is S of t, right? The complex envelope of the band pass signal is a what? Is a complex low pass signal. A complex low pass signal. Okay, so I wanted to underline this complex low pass signal and then complex envelope. Complex envelope is tied of T of what? Band pass signal. Band pass signal S of T is a complex low pass signal. So what is the need of mapping uh, this band pass signal to the complex low pass signal? Anybody can say why I did all this thing? Why I am mapping uh, the band pass signal to the complex low pass signal? Hope you're understanding my question. See, here I represented the band pass signal as what? Complex low pass signal, right? How I represented that as a complex low pass signal? By finding the complex envelope of the band pass signal, right? So what is the essence of this? Anybody? Yes, looking at the diagram of that complex envelope, is it possible to say or interpret anything? Yes, just I will show the, hope you noted now the sentence. Yes, my dear students, have you noted the sentence? I said the complex
Yes, sir.
envelope of the band pass signal is a complex low pass signal. Now I am asking, what is the need of mapping this band pass signal into a complex low pass signal? I am asking. At least looking at this diagram of, yeah, this is what the complex envelope, no? Right. Yeah. Is it possible to interpret anything from this? Hope you all know band pass signal, how I wrote. Then what is the complex envelope of that signal? So based on your understanding so far, what you have studied in the previous semester about AM, DSBC and other things. So you all know what is modulation. So for modulation, what are the things are required, right? I'm giving just hint. Is it possible to interpret the need of this? Yes, any one of you? Yes, it is. I said it is a complex low pass signal. Huh? What is a low pass signal is? With respect to modulation, low pass signal means what? Yes. Hope you understand my question. Low pass signal means what with respect to modulation? With respect to modulation, see, why do we go for modulation? What is the problem in transmitting the information as it is? You all know, no? The information signal is basically what? Is it a high frequency signal or a low frequency signal?
Low frequencies.
Yeah, see, information signal is basically a low frequency signal, right? So, which cannot be transmitted as it is because we have many difficulties. What are those difficulties? You all know. I think I need not repeat again. So you have understood or maybe there in your mind. So what will be the size of the antenna if at all I want to transmit the low frequency signal as it is, right? That's the first thing what we say. Antenna size will be very large if I want to transmit the low frequency signal. That is why we shift this low frequency signal to high frequency. With that, we will be able to reduce the size of the antenna. I hope that is the first and foremost requirement or why we go for modulation. Hope I am clear. Right? I think you can think of that example, right? If you take the low frequency signal and calculate what is the length of the antenna you require. And with respect to that, if you go for high frequency, then what is the size of the antenna, right? So keeping that in mind, what I wanted to stress upon here is the information content of the modulated signal, okay, is fully preserved in the complex envelope. That is what I wanted to say here. See, this is basically a low pass signal, na? Right? So in complex envelope, what I wanted to say is the information content of the modulated signal. Okay, the information content of the modulated signal. The modulated signal I represent as S of t. So that is basically a band pass signal. Okay, the information content of the modulated signal is fully preserved in the complex envelope. Okay, so that is why I would like to map this complex envelope of the band pass signal, okay, into a complex low pass signal. That is the first thing. That is the first requirement. And second thing is, see, analysis of the band pass signal is complicated by the presence of the carrier frequency, right? So the band pass signal will be far away from the origin, right? It is far away from the low frequency. So which will be appearing at carrier frequencies. So if I represent that as a complex envelope, then I have a signal which is not having the carrier frequency, right? So this complex envelope dispenses with the carrier frequency, and that will make the analysis as simple to deal with it. Okay, so dealing or even processing of low frequency signal is much easier than the processing or analysis of the high frequency signal. Okay, so that is the another reason why we are mapping this band pass signal into its equivalent complex low pass signal. Hope I conveyed the essence or need of representing the band pass signal as its equivalent complex low pass signal. Yes, my dear students, could you catch my point? I told you two reasons why we are interested in mapping this band pass signal into its equivalent complex low pass signal. Hope you got my point. Yes, I'm asking, hope you got my point.
Yes, sir.
Yeah. Okay, Ananta is saying yes. What about others? Yes, Manusri, could you catch my point, what I said?
Oh, yes, sir.
Manusri.
Yes, sir.
Yeah, can you repeat what I said? Can you tell the essence of mapping this band pass signal into its equivalent complex low pass signal? Yes, you said yes, no? Manusri, noise in background. Yes, you're not able to hear my voice properly. Okay, what about Ananta? You said yes, no, and can you tell? I think others are not speaking. I don't know what is happened to them. At least you said yes.
So the first point is most of the information is stored inside the complex envelope, and so we map it together. And the second one is due to the presence of the carrier signal, and also the information is stored away from the origin. Uh, we map it. That is what I understood.
Okay, fine. Thank you. So still I wanted to repeat once again, please be careful, be attentive, try to understand, because it is very catchy point, because you need to understand this, otherwise it will not have any meaning. Just doing this, right? Representing this band pass signal into its equivalent complex low pass, it becomes only the mathematical way. So what I said is the essence or need of mapping this band pass signal into a complex low pass signal is two things. One is, I said, the information content of a modulated signal, okay, that I call it as a band pass signal S of t, is fully preserved in the complex envelope. The complex envelope is basically a low pass signal, right? And even the information signal is also a low pass signal. Hence, I am interested in mapping this band pass signal into its equivalent complex low pass signal. Okay. The second thing is, I said the analysis of the band pass signal, okay, is complicated by the presence of the carrier frequency. Okay, the signal which is appearing at a higher frequency, the analysis of that will be complicated compared to the analysis of the low frequency signal. So this complex envelope signal, right, is with what? Dispenses with FC. Means it is not appearing at carrier frequency, right? So making the analysis of this complex envelope is easier compared to the high frequency signal. So that is the another reason. Okay. So you will appreciate the importance of this complex envelope. I think I will tell you further when maybe in the succeeding class. Okay. So now, hope you at least you are able to say now what is complex envelope, at least the mathematical expression as what? S tide of t, right? S tide of t is equal to what you can say? S plus of t, that is S plus of t is what? The pre-envelope of the bandpass signal into what? E power minus j 2 pi fct, right? Yes, is it clear? S tide of t is equal to S plus of t into e power minus j 2 pi fct. Or if you want to express in terms of pre-envelope, I can write S plus of t is equal to S tide of t into e power j 2 pi fct is the definition of complex envelope of a bandpass signal. Okay, so now let us try to understand the canonical representation of the bandpass signal. So canonical representation means it is the standard way of representing the bandpass signal. How do we represent the signal in a standard way? So here two things are there. One is by using Cartesian form. Another one is by using polar form to represent this bandpass signal. First, let me go with the Cartesian form. Okay. So the next topic is, I can say, canonical representation of canonical representation of bandpass signals. Okay. So just now we have discussed that the real part of the pre-envelope, right, is equal to what? Any one of you can say the real part of the pre-envelope is equal to what? Real part of the pre-envelope.
Band pass signal.
Yeah, bandpass signal, right? Just now I wrote the expression on the top. Fine, very good. So therefore, the bandpass signal is expressed in terms of its complex envelope, S side of the SA, right? So I rewrite here just now whatever the expression I have written there. So I can express S of t, that is the bandpass signal, as what I said, the real part of S side of t into e power j2 pi fct. Okay. So let me call this as equation 1. Okay. Fine. So I already said what is S side of t. S side of t is the complex valued quantity, right? So I can express this complex valued quantity, okay? Complex valued quantity in the Cartesian form. So this is the, what I can say, complex valued quantity, right? So I can express in Cartesian form this complex valued quantity as what? So Cartesian form, you are all aware. How do we write? Yeah, it is in the form of what? Anybody can say Cartesian form means? Yes, Cartesian form. Quickly, anybody can say.
X plus y.
Yeah, x plus y or x plus jy.
X plus jy, sir.
X plus jy. Good. So I can write this s tied of t, right? It is a complex quantity set. I can express this as in Cartesian form. It will be si of t, okay, plus j into sq of t, okay, plus j into sq of t. So this is in Cartesian form. You want me to write that in Cartesian form, I can express this complex valued quantity s side of t as si of t plus j into sq of t. So let me call this as equation 2. Equation 2. Okay. So what is this si of t and sq of t? Where Si of t and SQ of t are both real valued low pass functions. Real valued low pass functions. Okay. So let me prove this. How do I say SI of t and SQ of t are both real valued low pass functions? Okay. So now to do that, to understand how do I say this SI of t and SQ of t are both real valued low pass functions, we need to do some sort of mathematical this one. So let me substitute the equation 2 into equation 1. So can you substitute 2 in 1 and say what is the expression you get? Okay, substitute equation 2 in equation 1 to express this original band pass signal in canonical or standard form, what I can say. Okay, by substitute equation 2 in 1, okay, to express the original band pass signal, to express the original band pass signal in the canonical form. Or I can say standard form. The canonical or standard form. Yes, if you do that, what you're going to get. So wherever S side of t is there, you just substitute S side of t as Si of t plus j into Sq of t. So with that, I can write S of t is equal to real part of. So what is S side of t? It is Si of t, right, plus j into Sq of t. Okay. Yes or no? So this thing is multiplied by e power j2 pi fct. Okay. Yeah, now just expand this. So it is equal to what I can write, real part of, yeah, Si of t, right? Si of t e power j2 pi fct, then plus j Sq of t into e power j 2 pi fct. Is this fine? So what can I substitute for e power j 2 pi fct? Yes. Can I substitute e power j 2 pi fct as what? E power j theta is what? Yes, any one of you can say no. Some Euler's rule, you know what is the Euler's rule? E power j theta.
Cos theta plus I sin theta.
Huh?
Cos theta plus I sin theta.
Yeah, cos theta plus I sin theta. The same way we can substitute e power j 2 pi fct as what? Cos 2 pi fct plus j sin 2 pi fct, right? So with respect to that, I wanted to write here as real part of, okay, si of t. So just I'm substituting e power j 2 pi fct as what? I'm substituting that by cos of 2 pi fct, cos 2 pi fct plus j sin 2 pi fct. Okay, similarly for another term, or plus j into sq of t of what, cos 2 pi fct plus j into sin 2 pi fct. Okay, hope you have written this. Shall I scroll up? Yes, shall I scroll up? I am asking.
Yes, sir.
Yeah. Yeah. So just I think what I can write next, a real part of, just write si of t into cos 2 pi fct, right, plus j into si of t into sin 2 pi fct, to sin 2 pi fct. Then similarly the next term is j sq of t into cos 2 pi fct, right? Then next is what? J into j is j square. J square is minus 1. Can I write that as minus sq of t into sin 2 pi fct? Minus sq of t into sin 2 pi fct. Is that fine? J sq of t into j sin 2 pi fct. So j into j is j square, which is minus 1. So I wrote minus sq of t into sin 2 pi fct. Okay. So now I segregate real terms and imaginary parts separately. Then you can write yeah, I can, what I can write, I can write Si of t, right, into cosine of 2 pi fct Yeah, cosine of 2 pi fct, then minus sq of t into sine of 2 pi fct, sine of 2 pi fct. So, okay, this is one term. Then plus j of the remaining terms, that is si of t sine 2 pi fct, si of t sine 2 pi fct, okay, plus sq of t into cos of 2 pi fct. Okay. Yeah. In this, so I got in what format? This is the real part, first term, right? The second term is the imaginary part, right? So can I say this one is the real part, right? The first term is the real part, and the second term is the what? Is the imaginary part. Imaginary part. So with this, can I write s of t is equal to is what real part of that, right? So shall I write only si of t, that is the first term? Is that fine? Therefore, I can say S of t, it is the bandpass signal, which is expressed in canonical or standard form as what? Si of t into cos 2 pi fct, okay, minus sq of t into sine of 2 pi fct. So this is the canonical or standard form of representation of the bandpass signal. So what are this Si of t and Sq of t? They are real value low pass functions, I said, right? And Si of t I call is the in phase component. Okay, Si of t is the what? In phase component. In phase component of the bandpass signal. In phase component of the bandpass signal S of t. So if I write just BP signal, you understand now it is a bandpass signal. Okay. And similarly, SQ of t, SQ of t is the quadrature phase component of the signal S of t. Okay. SQ of t is the what? Quadrature phase. So this is the in phase, and this one SQ of t is the quadrature phase component. because SI of t is multiplied by cos of 2 pi of ct and SQ of t is multiplied by sine of 2 pi of ct. And you all know cos and sine are at what phase difference, right? They are at what phase difference between cos and sine? It is of 90-degree phase difference, right? So that is why something which is multiplied by cos is known as the in-phase component of the bandpass signal, and something which is multiplied by sine is known as the quadrature phase component of the bandpass signal. Hope I am clear, whatever I have thought so far. Yes? Yes, I'm asking, is this clear? How do I represent the bandpass signal in standard form or canonical form? So the canonical representation of the bandpass signal will be what? Si of t into cosine of 2 pi of ct minus sq of t into sine of 2 pi of ct. And now is it possible to say why I said when I wrote in Cartesian form s tilde of t as si of t plus j into sq of t, right? I said si of t and sq of t are both real valued low pass functions. Maybe during that time you might have got a question that, okay, to say real valued low pass function sq of t is with the term j, it should be imaginary. No one has got the doubt? When I wrote equation 2 in Cartesian form, I said s tilde of t is equal to si of t plus j into sq of t. No? So when I am saying it is a real valued, both the signals si of t and sq of t are both real valued low pass functions. So definitely at that moment, somebody might have got the question that the sq of t is with the imaginary part, right? So hope it is clear now. How do I say both are low pass functions? ಏನು ಹೇಳ್ತಾ ಇಲ್ಲ ಎಸ್ ಆರ್ ನೋ ಅಂತ.
Yes, sir.
Yes, okay. So I think it is 11:45. I have some more things to do. I think with this I will stop today. Okay. So at least now let us maybe in the next class, that is on Monday, I will be just saying how do we present this in the form of phasor diagram. Just have a look and come. Right. Phasor diagram, you all know no? How we write e power j 2 pi fct. How do we express that in phasor diagram? That is real and imaginary axis. No? So in the same way, we can express here also. Two things are there, right? Let us see how do we express in terms of phasor representation, and with respect to that, with respect to the phasor diagram, what will be the s of t? How do we get from that diagram? Let us discuss. Okay, so with this, let me stop my lecture for today's. And before I end up, I think I said I will tell about that sync function, right? If you have 2 minutes time, I will tell. What is the next hour you have?
Microwave theory, sir.
Microwave. Okay, then let me take up this that in next class.
Yes, sir.
Yeah. Okay. Yeah, I think all of you can write your USN in the chat box.